In the last video, we defined a relationship called congruency mod S, where S was a subring of a ring R, and we showed that that new relationship was indeed an equivalence relation. And at the end of the video, I posed the question, what are the equivalence classes for this new equivalence relation? So that's what we're going to be investigating in this video. Well, we need to set the stage. So we're going to let R be a ring and S be a subring of our ring R. I want to recall that A is congruent to B mod S means that A minus B has to belong to the subring S. And the question is, what can we say about the equivalence class that contains A? Well, let's actually investigate this simply by starting with the definition and see where it leads us. We know that the definition of this particular equivalence class is everything inside the ring such that A is congruent to that X mod S. So what I'm going to do is I'm simply going to let X be inside that equivalence class that contains A. And that's going to imply that X is indeed inside this set. And so what we now know is that A has to be congruent to X mod S. Of course, this congruency relationship is an equivalence relation, and since A is congruent to X mod S, that will imply that X is congruent to A mod S, since our relationship, our congruency mod S relationship, is an equivalence relation. And that's just the symmetric property of equivalence relations. But I also know that X is congruent to A mod S means that X minus A belongs to S. In other words, I know that there exists some little s inside set S such that X minus A is equal to little s. And so what that says is that we know that there exists an S inside capital S such that X is equal to A plus little s. And that last statement here says that X belongs to the coset A plus capital S. So I kind of want to think back to what we've actually done now. We've shown that if we start with an arbitrary element of the equivalence class of A, it winds up being in the coset that is A plus S. In other words, what we've shown at this point is the equivalence class for A is a subset of the left coset A plus S. Well, that raises the question, is this coset a subset of the equivalence class? Because if I can show this particular inclusion is true, then these two sets are actually equal to each other. So let's investigate the answer to this question. So our question is A plus capital S a subset of the equivalence class containing A under the congruency mod S relation? Well, to investigate that, we're going to let X be any old element of the coset. Well, what does that say? That says X is equal to A plus little s for some particular little s inside capital S. And what I want to notice is that that will definitely imply that x minus a is equal to that little s for some little s inside capital S, and that says x minus a belongs to capital S, which says that x is congruent to a mod s. And that's by the definition of congruency mod s. And what I want to remember is that congruency mod s is indeed an equivalence relation. So this thing here is true, will imply that a is congruent to x mod s. And that is since I know that congruency mod s is an equivalence relation. Well, what does that mean? That does say that x belongs to the equivalence class containing a, and that is because the equivalence class containing a is everything inside the ring such that a is congruent to it, mod s. So what have we shown here? Well, let's go back and think about what we've shown. We've shown that if we take an arbitrary element of the left coset, that arbitrary element will be in the equivalence class. So we are allowed to now say that a plus s is indeed a subset of the equivalence class containing a. And with what we had on the previous board, that lets us say that the left coset and the equivalence class are exactly the same thing. Well, what this means is that we can now say anything that we know about equivalence classes applies to cosets. And I kind of want to think about what that means. So, since the left cosets equal the equivalence classes, everything we know about equivalence classes applies to left cosets. And in particular, what that means is that the equivalence class theorem says that two equivalence classes are either equal or they are disjoint. And so what we can say is that if A and B are inside the ring R, then their left cosets are either equal or their left cosets are disjoint. And to make that a little bit easier to read, let's put parentheses around that. And then let's see, what else do we know? There's something else that we know. We know that the we know that the equivalence classes, so the set of these guys such that A is inside R, that thing partitions the whole ring R. And since the equivalence classes are the left cosets, we also know that the left cosets partition the whole ring R. And then the final thing that I want to look at, because it's intimately connected to the left rather to the equivalence classes, is I want to look at this question. When is A plus S equal to B plus S? Well, the easy answer to that is A plus S will equal B plus S, happens if and only if the equivalence class for A is equal to the equivalence class for B, but that means that A and B are equivalent mod S, and that says that A minus B has to belong to the subset. So the final thing that we want to say about these left cosets is that we know as a little theorem that two left cosets are going to be exactly equal to each other if and only if the difference of their representatives belongs to the subset that we are looking at the cosets of. And that will complete this video.